talk for today is Semon Rezchikov, and he's going to tell us about.
Hi, everyone. This will be sort of an algebraic talk. I've talked about this paper before, but it'll actually be out next weekend, or sorry, this weekend. First I have to say something about spectra. Does this? No, sorry. There we go. So spectra. Okay, great. Spectra. These are like spaces, but more algebraic. So I'm going to very quickly tell you what you need to know about these for this talk, because otherwise it's sort of impossible to talk about this stuff. So if you have a pointed space, I mean, all my spaces have the homotopy type of a CW complex, then you get some spectrum, which is a suspension spectrum. And the homotopy category of spectra is triangulated. And it contains inside of it something you can pretty easily describe, which is the category Spanier-Whitehead spectra, which has objects, sigma A X. Can you project? Hi, can you guys hear me? No one can hear me. Please tell me. You can't hear me? No? All right, I'll be louder. Is this okay? Great, thank you so much. If you can't hear me, or if I write something that you just can't read, just like yell it out. Thanks. So Spanier-Whitehead spectra are objects which are kind of formal suspensions or desuspensions of a space, and maps between them. So a map from sigma AX to sigma BY, these are just the colimit of homotopy classes of maps of sort of arbitrarily large suspensions of these objects in spaces. And the point is this stabilizes, and so this is some triangulated subcategory. And moreover, the homotopy category of spectra is symmetric monoidal. With unit, the sphere spectrum, which is just the suspension spectrum of S0. Okay, and so this is some triangulated category, which you can kind of understand by this big little piece built out of spaces. But in fact, it's the homotopy category of something. There are many things that it's a homotopy category of. There's a nice model. There are many possible nice models for spectra, but one of them is orthogonal spectra. I'm not going to really say what these are, but these are some kind of functors from some simple category. I don't know, I'm going to call it curly T to spaces. And then, this category, the category T is symmetric monoidal. So these functors have a symmetric monoidal product by Day convolution, and that gives you the symmetric monoidal structure on the homotopy category. The point is there's some model structure on orthogonal spectra, which you kind of invert certain weak equivalences, and that gives you actual spectra. Okay, so that's one thing to say. There's some kind of concrete way of describing these objects. You can get them from spaces, but also you get them from cohomology theories. So if kind of the functor, does this work? Yes, it does. The functor from a space to the space of maps from its suspension spectrum to some other spectrum is a cohomology theory. And spectra define cohomology. Cohomology theories can be used to define spectra. And in particular, when your cohomology theory has some nice multiplicative structure, often that's reflected on some structure on the actual representing spectrum. So for example, there exists some spectrum HZ representing cohomology. With integral coefficients. And so cohomology is a cup product, which is commutative, and so this is a commutative ring object. Close this thing. No. And so you can talk about modules over this thing. This makes sense if you have a commutative ring in a category. And you can talk about the homotopy category of these things. And this is the derived category of the category of integral chain complexes. Okay? And so the point is, from this, you can just, like, if you want to do homological algebra, the most sort of generic homological algebra constructions can be done with spectra directly. And sort of things that you might know about in, like with chain complexes, make sense in a lot more generality. So for example, can do so for example, delta here is the category of finite sets, or finite totally ordered sets. And maps which preserve the total order. This, of course, contains things like n, which is 0 less than n. And so there's a simplicial object as a contravariant functor out of this category. And so the Hochschild, if you have an associative ring spectrum, so maybe if you have R is a commutative ring spectrum, and A over R is an associative algebra in spectra. So this all makes sense because of the previous words I said. You could define this simplicial object, which sends to tensored over R n+1 times. And then, there's like some maps of inclusions of finites, sort of maps of these finite sets, which basically on the functor sends this to either multiplication or dropping something or, insertion of units. Sorry, my rings are always unital. And then you take the geometric realization of this simplicial object, which I'll write down in a second, and this is the Hochschild homology of A over R. Okay? And what this means, this is something like, just so you have a sense of it, so if you have a functor to spaces from some category, you can always just take the product of that functor level-wise with some other space. So I can write delta cross, I can write a space producted with a spectrum. That makes sense. So this is something like the coequalizer of the following things. So you take delta n cross A smash. So remember, this is the symmetric. This is the monoidal structure. Smash R n+1, and there's two maps. And you take the product. So you take the disjoint union over n, disjoint union over n m. So there's two maps. So on one hand, if you have a map, so there's this functor from delta to spaces, which sends n to the n simplex, right? Just by kind of moving where the vertices go. And so there's these two maps. You have you either act by a map in the category delta on the m simplex, or you kind of pull back by the contravariant functor on that map on the simplicial object. So that defines these two maps in this coequalizer diagram, and you take their coequalizer. That's the geometric realization. In other words, you're just like gluing together these spectra according to some rules. Okay. So if you took R to be Hz, and then A was something that corresponded to, an associative DGA, then this would give you some Hz module, which would be equivalent under the previous equivalence to like Hochschild homology. Okay, so this is some basic construction. And similarly, you can also define Hochschild cohomology in the world of spectra. which I'm going to write with this little superscript. So this is the geometric realization of some co-simplicial object, which is a covariant functor from delta to something. Sorry. And so that to get what this is, you just dualize the previous story. So this is some equalizer. So F here means like R linear maps. There's some function spectrum, okay, which you can define by everything I said. So something like functions from delta n to this other guy. And there's two maps, again, either by, and I'm not going to write what goes here. You either act on the delta n or you act on the value of the cosimplicial object. You take the equalizer. Okay, so there's some notion of Hochschild homology of associative ring spectra over commutative ring spectra. And there's some notion of Hochschild cohomology, and these generalize the usual notions. So the formulae are just the usual formulae, but you replace the word chain complex with the word orthogonal spectrum at every step, okay? And so there's also famously a cat product. So Hochschild cohomology acts on Hochschild homology. So for this now, I'll say something that maybe is a little easier. It's more immediate and kind of nice and geometric. So I want to explain how that works. So there's something, so if you have the n simplex, we can take its prismatic subdivision. So we can write the n simplex as a union over pairs a plus b is equal to n of non-negative integers of products of simplices. Okay, let me draw the simplest picture. So n is 2. So this is, you take this simplex and you subdivide it like this. Okay, you divide it into like the top guy, delta 0 cross delta 2, the bottom right guy, delta 2 cross delta 0, and this diagonal thing, which is delta 1 cross delta 1. Okay. And you know, there's some formula for this. This is really some like functorial nice thing. So the map from, so if you think of delta n as, I'm trying to give you the sense of like what kind of math this stuff actually involves. If you think of delta n as tuples, t0, tn, in Rn plus 1, greater or equal to 0, so that the sum of the ti is 1, the intersection of this hyperplane with the positive orthant, then the map from delta a cross delta b to delta a plus b is the following one. You take t0 dot 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 ta, t1, oh sorry, S0 dot 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 SB, you map it to 1/2 T0 dot 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 1/2 TA minus 1. Then you average the next ones, 1/2 TA plus 1/2 S0. And then you go kind of 1/2 S1 all the way to 1/2. Oh, sorry, you need to add something here. 1/2 TA plus 1/2 S1. And then all the way to 1/2 TA plus 1/2 SB. So you have two things that sum to 1, and you just kind of concatenate and average them, okay? This defines a map, and you choose these over all pairs A and B, and this divides the whole simplex. Let me make sure I got that formula right in case someone's checking it live. Oh, yep, that's wrong, sorry. You only average in the middle coordinate, and the rest of them you don't. There we go. Now this makes sense. Sorry about that. Okay, so this is some cool, nice subdivision. So let me tell you how you define the cat product. That's sort of fun and concrete. So suppose you have a function from delta A to functions from copies of your spectrum to your spectrum. And you also have a bigger thing, delta A plus B, and A plus B copies of your spectrum. Okay, so you write this guy on the right as delta, a union of these pieces, delta A cross delta B, smash A to the A, smash A to the B plus 1. And now you can, take this thing and apply it to this piece, right? And now you get delta B smash A, smash A, smash. Okay, this is minus B minus 1. And then you can multiply in here, and you get delta B smash A, B. Okay, so this is like, if you remember the formula for the cap product in Hochschild homology, the cap product in Hochschild homology would be something like you have a function, tensor A0 bar A1 AN is equal to A0 F of A1 AR bar AR plus 1 ... AN. And this is just how you make sense of this with spaces. Okay, great. So you check this prismatic subdivision has exactly the right relations to give you a map from Hochschild cohomology of A over R tensored over R with Hochschild homology of A over R to Hochschild homology of A over R. Okay, so that's what something like a cap product looks like in this world. It's given by this kind of completely explicit formula. Okay, so now I'm going to say, any questions so far? All right. So now I'm going to say something else. I'm going to say something about equivariant spectra, sort of briefly. So here G now is some finite group. Or actually it's a compact Lie group works, but you should think of it as a finite group. That's mostly the case I need. And then we want to replace, spaces with G spaces everywhere. And the important part is that we think of, if we have a G map between G spaces, we want to think this is an equivalence when, if you look at any closed Lie subgroup, the induced map is an equivalence. Okay, that's our notion of homotopy equivalence. So that makes sense for G spaces, and then somehow spectra are just like some souped up version of spaces. And so this gives you some notion of, well, if I had what would be a G spectrum? So I said, orthogonal spectra are just functors out of some category to spaces, and now they're functors out of the same category of G spaces. So they're just, spectra with a strict G action. But the point is that, this tells you how to detect weak equivalences. So there's some model structure which is an analog of this for G spectra. And one way of talking about this is that there is this fixed point functor. So if X, the G spectrum, then you have this fixed point functor XG, which is categorical G fixed points, or genuine G fixed points. Actually, it makes sense for any H. And then this is an ordinary spectrum, and you can take homotopy groups of this object. So x to y is an equivalence when pi I xh in this genuine sense to pi I yh is an isomorphism for all I and h. Okay, so that's how we detect weak equivalences. And the thing to say here is that in this world, so before in spectra, the functor of suspension on spaces becomes invertible. So this is smash product with S1. Corresponds to taking a chain complex and shifting it up and down. In this world, so there are these, if you have V, if V is a G representation, a finite dimensional G representation, then you have this special like G spectrum, which corresponds to the G space SV, which is the 1-point compactification of V. And now you have this functor sigma V, which is the smash product with SV. And now this is invertible. So in the world of G spectra, you can suspend and desuspend by representations. That's somehow essential. Okay. And I'll say just a little more general stuff before I actually start talking about something substantial. So I said there's this notion of categorical fixed points. That's supposed to be one analog of taking fixed points of spaces. There's also like 3 other notions. They're all related in a simple way. Okay, so another notion is geometric fixed points. So this takes a G spectrum and so first, you can always forget the action to a subgroup. So now I'm going to not talk about H anymore. I'm going to write it this way. This is phi H or phi G. And what this is this is supposed to be like the actual notion of taking fixed points on spaces. Not the one, but it's like this sort of the other one is about like maps to something, and it's kind of about homotopy groups. This one is defined by the following 2 properties, or maybe 3 properties. First of all, that if you take a suspension spectrum, you add it just to joint base point, you take a suspension spectrum of a G space, and you take geometric fixed points. Then this is the same as taking fixed points of the underlying space, and then taking suspension spectra. And it's also monoidal and commutes with homotopy colimits. And these characterize this functor. So I'll say a little more in a second about like one example of this, which is sort of enlightening. There's also homotopy fixed points. So this takes, this is denoted like this. And this is just, okay, so I said you have a spectrum, and it's like an orthogonal, the G spectrum is like a G orthogonal spectrum is literally a G orthogonal spectrum. It's an orthogonal spectrum with a G action. And so there's this diagram from this category, point with endomorphisms given by G to the category orthogonal spectrum. And we just take the homotopy limit of this diagram. Okay, that's homotopy fixed points. There's also homotopy orbits. And that's denoted this way. And that's the homotopy colimit of this diagram. And then there's a map from one to the other called the norm, which I'm not going to explain. And its cone, they said this is spectra are triangulated. These are all spectra, is the Tate fixed points. And Well, the point is that if X is an HZ module, then I said all these sorts of things are kind of correspond to computations in chain complexes. And so this sequence above is the long exact sequence of Tate cohomology of a sequence of G chain complexes.
Sorry.
Yeah.
Is the norm map well defined even when G is not finite?
No, I think here G is finite. Thank you. I mean, there are some other examples like for S1. Actually, wait, no, it's actually always well defined. Sorry, there's this pretty general construction in yeah, I think it's always well defined, but I only care about it for G finite and GS1, where it's a lot more explicit and sort of classical. Okay. Okay, so said lots of words, but this tells you how to compute some of these words in a bunch of examples. And let me give you another place where you can compute these things. So now this is the Tate square. So here I'm going to write this just for G equals CP. There's a much more general version. So the genuine fixed points, this is the fiber product of the geometric fixed points and the homotopy fixed points over the Tate fixed points. Okay. This is just some statement. All right. And what do I want to say about this? So I'm not telling you what these maps are. You should just know about it. But the point here's kind of an important like little example of why some of these, like how these different notions behave. So you always have a map from genuine fixed points to the underlying, to the spectrum if you just forget the action. But there's no map from geometric fixed points to the spectrum if you forget the action. And the reason for this is because if you take S, so I said you could suspend by representation, so you can also desuspend by representation. And then you take geometric fixed points. Then by symmetric monoidality and so forth, this has to be the same as taking the invariant part of the representation and desuspending by that. So if you think of like desuspension as kind of shifting dimension down, then now taking fixed points sort of increases dimension. So that's sort of awkward. So that's sort of what, there's no natural map, no geometric fixed points of something to the original thing. For spaces there is, but for spectra there isn't. And this is the essential reason why. All right, so that was a lot of words. Now, the main thing that you get out of spectra, besides all these very complicated formulae, is you get some things that make sense in spaces but are harder to make sense of algebraically, but they continue to make sense of in this relatively algebraic context. So there's something called the diagonal. Okay, so this is the HHR diagonal for Hill, Hopkins, and Ravenel. So if you have a spectrum X, an ordinary spectrum, then you can take X, smash it with itself P times, and now it's a CP spectrum. And there's a diagonal map like this, which is an isomorphism onto the geometric fixed points of this thing. And the point is that if you had a normal space, you took P copies of it, then the diagonal is the fixed points of the CP action on P copies of the thing. And then there's a generalization of this to all spectra, okay? So this map, if you think about it in terms of chain complexes, is pretty complicated. If you have the chain complex, you take P tensor copies of that chain complex, then, you know, what's the kind of, like, how do you make sense of the diagonal inside these P tensor copies? Well, it's certainly not literally like X tensor X tensor X. Those things don't, like the degrees are all messed up. But nonetheless, if you think of that thing as a spectrum, then there's some replacement for this. Okay. And I just want to say something. So if there's there's some relationship between this, actually, I'll say this later. Okay. So another thing you get is you get this notion of a cyclotomic spectrum. So the dumbest possible notion is you just say that your spectrum is equivalent as an ordinary spectrum to its own CP fixed points. So maybe if your spectrum had an S1 action, then this thing has an S1 action, and then this thing has an S1 mod CP action, and then it's supposed to be equivariant with respect to this data. And sort of the canonical example of this is the suspension spectrum of a free loop space. Because the underlying space has this property. Because if you have a loop in something, you can take its p-fold cover, and that's the same as the CP fixed points in the space of all loops under the loop rotation action on the space of loops. Okay? So this is kind of canonical example. The free loop space has the suspension spectrum of the free loop space has this nice property that it's the same as its own geometric CP fixed points. And there's another example, which is if you take any associative ring spectrum and you take its Hochschild homology over this here spectrum, then it also has this property. And the reason for this is, so I'll just tell you what this construction looks like. It's, again, very, very simple given what I said. So there's something called the edgewise subdivision. So what you do is you take an n simplex, and you just subdivide the edges like this. And then you subdivide it into a bunch of new simplices. Alternatively, if you have a simplicial object, well, if you have this category of finite sets, you can send this set to the following set. You take 0 less than n, less than 0, maybe prime, less than ... less than n prime, less than, and so forth. You basically make p copies of your original set, and you just stick them together. So then if you have a simplicial object, you can pull it back by this functor. You get a new simplicial object. That's the p-fold subdivision, of edgewise subdivision of that object. And so you have that, if you take the geometric realization of a subdivision, it's the same as the realization of the original thing. So to define this map from HH over S to its geometric fixed points, I can just define it level-wise, because it's just a colimit, so geometric fixed points commutes with colimits. And it's just like the diagonal map on every level. So you send delta n cross a n to delta n cross a, I guess, pn, which is what happens when you pull back the original simplicial object by this SDP map. Okay, so that's all this is. The point is this is an equivalence because it's an equivalence level-wise. Okay. So now I'll say something like some actual theorems. So first, let me tell you a fun fact. Okay, this is a nice bit of combinatorics. So, okay, I said I can take a simplex and I can subdivide it into products of simplices. I can also take that's the prismatic subdivision. I can also take a simplex and subdivide it into lots of copies of itself, like 2 to the n copies of itself. Or the p to the n copies of itself. That's the edgewise subdivision. But there's also the Eilenberg-Zilber subdivision. So if I take a bunch of products of simplices, I can subdivide it into simplices again. That's what gives you the, that's the Eilenberg-Zilber map in singular homology. And so this is a cute fact. So if you take delta n, when you take this prismatic subdivision, delta A cross delta B, and then you take the Eilenberg-Zilber subdivision, and add lots of copies of delta n, or you take this edgewise subdivision, then these are the same thing. Okay, so the picture is you take this triangle, and then here it is. And then that's the Allenberg-Zilber subdivision of delta 1 cross delta 1. Okay, there's some generalized version of this picture. All right. So now what I want to tell you is I want to tell you how this cap product and this cyclotomic structure are related, and then maybe do something with this. So here's how this works. So I want to define some sort of p-fold version of the cap product. So this is something like okay, so I'm going to drop the base ring R here. So you have HHA cohomology smash HHA to HHA. But I want there to be P times that I take the cap product, and I want to say that this is a map in CP spectrum. Okay? So how would you do this? Well, here's the idea of the formula. You take F1 kind of, let me erase this. You take P functions, and then you take a big tuple, right? So this is the p-fold subdivision of the Hochschild chain complex, if you think about it. And then you just use the formula for the cap product p times. So this is x0 f1 of x1 dot 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 xa bar xa plus 1 xn. That's the first copy of the cap product. Then the second copy of the cap product, you do it here. Maybe A1, A2, X prime, A2 plus 1, dot, 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 and so forth. So in each of these pieces of the circle, you just do the cap product once. Okay? And this gives you a map like this from F of A, maybe M copies to A. You have P copies of this mapping spectrum. Smash A n plus 1 P to A n minus M plus 1 P. Okay? Like if you just interpret this formula in the obvious way. So this bar thing, this is like a lot of tensor copies of A, and the F's, these are copies of this, P functions from A to the M to A. All right, so this looks like what? This looks like you have some co-simplicial object, smash some simplicial object, to, there we go, Y. It's supposed to be Y. To the simplicial object. So these are a bunch of maps like this satisfying the identities of a cap product. So again, this prismatic subdivision trick, just you take these maps and this defines for you a map like this. Okay? And this is a CP map because all these maps are level-wise CP maps. And now you can take, so I'm going to call this cap P. Okay? And now you can take geometric fixed points of this equivariant cap product or Tate fixed points or whatnot. And there's this, so this previous fact that I said now lets you compare this to something in the literature. So you take cap P, TCP, and you do this, say, where R is Z, or some kind of classical commutative ring, then this formula appears in literature in Zihong Chen's work. You need to use this previous fact to actually do the comparison. It's just this formula looks different. So in other words, if A was a Fukaya category, and you applied this operation on TCP of this Hochschild homology, then you would get something which you can then compare under the open-close map to something called the quantum Steenrod operation on the underlying symplectic manifold. Okay, so then maybe R equals FP here. Sorry. Okay, so I'm talking about something that exists in geometry. All right, and now I said that, so this thing has this kind of property that it's a cap product, a cap-like product. And so to check that I have a map of such data, I just need to check it level-wise. And so there's this easy diagram to write down. On the top, you have this cap product. On the bottom, you have this slightly more complicated thing, this p-fold cap product. And then if you take geometric fixed points of the bottom thing, everywhere, you take diagonal tensor diagonal here, then this diagram commutes. Okay, again, this is like totally elementary from the definitions if you just unwind them. So what this tells you is that the following, you have this relationship between the equivariant cap product, the usual cap product, and the cyclotomic structure map. Okay, so I'm going to write down this formula. So this looks like this, TH, okay. I'm going to write everything is over the sphere here. So Hochschild cohomology of A over the sphere, tensor Hochschild homology of A over the sphere to Hochschild homology of A over the sphere. And here you have this cyclotomic structure equivalence. And here you have delta smash cyclotomic structure. The claim is that the previous thing immediately implies that this diagram commutes. Okay, so this looks very abstract, but I guess then you can just compute this in various cases and you realize it gives you a formula in Cartier's paper. That's the name for the reason for the name for the talk. So what you can do is you notice that, so first of all, you can go PCP to TCP. So the same thing holds, bifunctoriality. And then you can, I just want to say this right. So yeah, you can take, there's this map from FP to FP TCP, kind of the inclusion of the unit. You can smash this whole thing with that. And this whole, the vertical lines are all linear with respect to this map. And so you can take the adjoint map with respect to this. Well, maybe I'll just say that if you take this formula, you take A to be like the spherical Laurent series ring. And then from it, by doing some algebraic manipulations, you can extract this some interesting formula of Cartier. So I can write it down. It's sort of fun. So if you have the point is, these are like vector fields. These are like differential forms. And so the cat product is like interior product. And so what you expect is you get some formula related the interior product and some kind of Frobenius. And when you work this out, you get exactly a formula like this. So if you take a ring, if you take a commutative ring A, which is smooth over FP, then there's this isomorphism from differential forms on A to the algebraic de Rham cohomology of A, which Cartier defined. And there's also this map from vector fields to vector fields. Where if you take a vector field V, just apply it P times as an operator, as a derivation. And this is another vector field, okay, by the Leibniz rule. And so what the above formula boils down to is the following formula. If you take I of V to the P of closed differential form, this is the same as I of V to the P, actually, no, let me, oh God, I might forget how this goes. Sorry, it's this formula. You have Cartier inverse I of V Cartier is equal to I of V to the P plus or minus P copies of the Lie derivative. I of V. I think that's right. Okay. Somehow this previous formula boils down to this other one. Okay, so it lifts this. This is in Cartier's paper, where he introduces this thing. And it lifts it to kind of arbitrary ring spectra over arbitrary commutative ring spectra. Now let me say a little bit about why you might care. I started a little late, so I'll just go to like 5:35. Hopefully that's okay. Okay, so calculus mod P. Okay, so you can take Hochschild homology over the sphere of Laurent series over the sphere. And this maps to Laurent series, right? Because you can take differential forms and basically project them to zero forms. And you can take the cone. And you get something that looks like Laurent series again, shifted up twice, but it has a different circle action. Okay, so Hochschild homology is a circle action, so this all works. The way to understand this is that it's like Hochschild homology of an algebra is like, so if you have Laurent series is like chains on the circle, chains on the base loop space of the circle. So Hochschild homology should be like chains on the free loop space of the circle. So this looks like the suspension spectrum of the free loop space of S1. And here you're mapping it to the suspension spectrum of pi0 of the free loop space of S1. And you think a little bit about what this means, and this means that this piece is the direct sum over n of S v to the n as a S1 spectrum, where v to the n is the S1 representation, where z acts by its nth power. Okay, so the idea is that this, the nth piece here, this is like x to the n dx over x. Okay, so the differential form dx over x doesn't, so somehow this one form, x to the n dx over x, is an interesting circle action. when you think about it in terms of spectra. And this is kind of governing some of these number theoretic properties of kind of calculus type phenomena in characteristic P. This is somehow a very old computation, but also worth saying. And so you get this diagram. So from this maps to the same thing. TCP. This maps to, again, the same thing, TCP. Here, the circle action is trivial, and so CP is the group with the elements of order P inside the circle. So this I'm going to think of as one forms on this Laurent series ring. So shifted up by 2, I guess. So this maps to here, to one forms shifted up by 2. And like this map on the right is defined as the map fitting to make this a map of exact triangles. And you can compute everything by just basically computing integral homology of everything or smashing everything with HZ. So this map then, this is the Frobenius map. And this is exactly this Cartier map. So this sends x to the p and dx over x to dx over x. Or another way of writing it, it sends d of x to the p to 1 over p of, sorry, it sends dx to 1 over p d of x to the p, which would be 0 mod p if you, okay, this should be, take the tensor product with HFP. So you would like take d of x to the p, but it's 0 mod p. So if you divide out the p, then it's not 0. All right. So this is this diagram of just, and it has lots of extra structure. Like this is a map of rings. This is a map of rings with S1 action. This thing has a section, but not S1 equivariantly, and so forth. There's lots and lots of structure in this diagram. But what you do with this is you do one more thing. All right. So if you have a category C over this Laurent series ring, then you can form the following, you can use the following formula. So you can take THH of C, and if you tensor it over, okay, so THH, I'm just going to stop doing this, of something is Hochschild homology over the sphere spectrum. So there's this formula. Okay, so if you take absolute differential forms and you have tensor functions and you get relative differential forms. So basically you take, this thing and you tensor it over this thing with this exact sequence, okay? With this earlier exact sequence. There we go. Yeah. We tensor absolute topological Hochschild homology with this earlier exact sequence. And what we get is we get a map as part of this sort of second map here from Hochschild homology of C over S x x inverse to something like it shifted up by 2, but with a different action. Okay, and this is some mysterious map, but now what you can do is you can tensor everything with Z. And now you get maps that are well known in Hochschild homology. So if you forget the S1 action, so then this is cap product with a class kappa, where kappa is a class in HH2. So this is the Kadir-Spencer class, or the of this family of categories. So this kind of pops up in symplectic geometries, the Caladian class sometimes. Or this is the Borman-Sheridan class if you deform a Fukaya category by a divisor. Then if you kind of take TS1, so then what you get is you get the Getzler connection. This is the Getzler connection of a family of categories over the Laurent series ring. Okay, so this is a non-standard presentation of these more standard notions. Okay. So I'm just going to say the last thing. So what we do now is we take this diagram, we tensor it with FP to FP-TCP, like this. And then we just compute what happens when we take, Hochschild homology of C, and then we tensor it with this whole diagram above, okay? We just compute it. And you get some new diagram, which looks like this. So you get, this uses some just sort of standard, but somewhat non-trivial results. So now what you have is you have a, just want to state this. So now let's say C bar is over FP x inverse, and say it lifts to S 1 over N, x inverse. Okay, so you have a category over sort of a finite characteristic that happens to lift to the sphere. Then you have the following commutative diagram. There's some map, so you have Hochschild homology of C bar. Okay, so I'm going to call this ring R now. Over R, Frobenius pullback, tensored R, RTCP, to Frobenius pullback one forms here. So now here all the actions are trivial. So taking take homology just adds on some extra variables. It doesn't really do anything. Okay, so here, this is the Getzler connection. So I said that's usually, but you add on this extra variable theta, because if you have a chain complex mod P, you take homology with respect to CP, that's the same as taking take homology with respect to the circle action, adding on an extra variable. And here what you have is there's some canonical connection associated to multiplication by this kappa class. So if you have any endomorphism of a module over this ring R, you take Frobenius pullback, that thing has a connection. This is the canonical connection. This is called the Higgs transform or something of a connection in characteristic P. And so then you can compute the p-curvature of this. So I'm going to say what this is. I'm going to end my talk. So p-curvature is, you can think of it in the following way. This is if you take it in the QDQ direction, this is just the operator, you differentiate p times and you subtract the original thing. Or in general, it measures the error between taking p powers of a vector field and differentiating in the direction of that vector field. Okay, so that tells you that the p-curvature of the Getzler connection is the conjugate of the above by this map phi. Sorry. But then the earlier formula, if you, again, tensor with FP and do some manipulations, tells you that this is exactly this equivariant p-fold cap product. Okay? So then, if C was a Fukaya category and it happens to live to the sphere, then these sort of standard comparison results comparing the Getzler connection to the quantum connection, cap products in Hochschild cohomology and Hochschild homology to the quantum product, Zihong's work on comparing this equivariant cap product to the quantum C-naught operation would tell you what the p-curvature of this quantum connection is in that case. And there's some family of examples where you can apply this because people have worked out some cases where like the Fukaya category actually is defined over the integral Novikov ring. So this gives you, this whole very algebraic discussion actually gives you some enumerative consequences. But I wanted to explain like what the algebra actually looks like. So I'll end here. Thank you.